Hello everyone, my name is Vaibhav. I'm a second year BTech student at IIIT Hyderabad, and today I'll be presenting the topic of integration. Specifically, we'll be solving the first exercise of this chapter, and I'll be giving a brief introduction about the topic before starting with the exercise. So let's begin. So integration, you can see the notes are on the left side of my screen. So it is usually mentioned that it is the opposite of differentiation, but it does not give a particular good image about it, does it? So let us start from the basics. For integration, to be able to understand the concept of integration, we need to understand differentiation first. So as you would all know, from the first principle, we can write the derivative of function fx with respect to x in the following form as limit h tends to 0 fx plus h minus x upon h. Uh, so we can write it in this form where we can write the denominator as x plus h minus x, and now we can use the notation like x1 is x and y1 will be f at x1, basically fx, and x2 will be x plus h and y2 will be fx. So basically you can write the derivative as y2 minus y1 divided by x2 minus x1. Now you would notice that this is also the form of the slope of a line, and hence this is simply the formula for the slope of a line passing through x1 y1 and x2 y2. And since h is very small because its limit tends to 0 as we saw before, therefore x2 is just a little greater than x1. Therefore, the part of the function between x1 y1 x2 y2 can be approximated as a straight line, as I have shown in the diagram. Thus, differentiation is nothing but the slope of the function at x, or equivalently x1. So I hope the concept of differentiation would be clear at this point. If not, I'll share these notes so you'll be able to uh, reread them and understand. So I am assuming everyone is clear with differentiation. Before continuing, it is strongly advised to go to the NCERT for integration. So yeah. So now let us come to integration. So consider a function gx defined over the set of real numbers. Let x1 be a point in the domain of gx. Let us consider a quantity a1 which is given by dx1 into dx. So just consider that a1 is just some quantity. We will try to use this quantity for deriving some things. So a1 is equals to gx1 into dx. So let us try to visualize what a1 might mean. So consider a rectangle of height gx1, the value of the function g at x1, and width dx. Dx is a small change in x. So next, the area of this rectangle will be equal to a1 because area of rectangle is length into breadth. Here the length can be considered dx and the breadth to be dx and vice versa. Hence a1 denotes the area of a rectangle. So specifically which rectangle we'll see later. So let us see the curve of the function gx. Let us consider the region of the graph between points x equals to x1 and x equals to x1 plus dx, which looks somewhat like this. If this is the curve for gx, then this region would denote the area between the x1 and x1 plus dx, area under the curve. Since dx is extremely small, so here in the diagram I've shown it pretty enlarged for clarity, but it will be extremely small. It will almost be a straight vertical line. You can convince yourself that the shaded area is approximately a trapezium. We can write its area like the following. So you know the area of a trapezium is half into sum of parallel sides multiplied by perpendicular distance between the parallel sides, and this we can write the area of the trapezium like this. We can further simplify the above approximation to make our lives easier. Notice that fx1 and fx1 plus dx are approximately the same. It's again because the gap is very small, and hence fx1 and fx1 plus dx, these two values are almost same. And therefore, we can write fx1 plus dx as just fx1. And simplifying further, we'll just obtain a equals to fx1 times dx. Now you might see that this is similar form as the a1 we obtained here. So you can see that this a1 was nothing but the area of the rectangle. So we basically have done an approximation that this area is equals to the area of the rectangle. So If we sum these small areas over range x1 to x2, we can just calculate the area in the curve between point x1 and x2. So in our original function g, and when we had gx1 times gx, we could just sum over these areas from a range x1 to x2. And this would basically denote the area under the curve, because we are summing up small rectangles like these from in a given range. So now we cannot simplify this any further with just this much information. So let us assume that gx is the derivative of some function hx. That is to say that let there be some function hx, and the derivative of hx will give us gx. Then we can call hx to be the antiderivative of gx. So like we could say that gx is the derivative of hx, gx is the derivative of hx, just like that hx is the antiderivative of gx, just the opposite. So we can write the small area A that we had earlier as A equals to d of hx into dx, right? And simply as A equals to d hx, because the dx term would cancel. We could write this because as you can see, this had, so it had gx1 into dx, and uh, we had just this, so hence we can write it as dh. It should be specifically dh at x1. So I think I forgot to include that. So dh at x1 divided by dx is equals to dx. The derivative of hx at x equals to x1 is dx. So we can just write dx1 as derivative of hx at x equals to x1 times dx, and we'll obtain this. And we'll simply obtain this after simplification. Now, if we were to sum the areas from x1 to x2, basically this summation would reduce to just summation over dh xi. So now the value of dh xi is just the difference between xi plus dx and xi. So h of xi plus dx and xi. So for an intuitive understanding, you can write it like this. So hx1 plus dx minus hx1, hx1 plus 2dx minus hx1 plus dx, and so on. And you could intuitively understand that this would reduce to hx2 minus hx1, because basically we are summing up the small d hxi, then it would basically mean summing up over small increments in the function value. So this is summing up small changes in the function value dhxi from hx1 to hx2. Therefore, we'll obtain the difference between the two values. Now we have a simplified expression for the area under the curve of gx in terms of the value of its antiderivative hx at the two points. So we have a simple expression for the area of the curve, area under the curve. This is the core idea behind integration. We replace the summation sign with the integral sign to denote the summation of very small values. But the only the integral sign is nothing but summation sign. And thus we can write A total is summation or integral from x1 to x2 gx times dx is simply hx2 minus hx1, where h is the antiderivative of g. So the problem reduces to finding this antiderivative function. If we have the antiderivative, then we can find the integral of any function that is given to us. So there are certain rules as to how we can evaluate this antiderivative. These rules are given in the NCERT textbook, and I strongly recommend you to get familiar with them. I have included those rules directly taken from some of those rules. So basically, some basic functions like derivative of tan x will give me sec square x. So hence the antiderivative of sec square x must be tan x. Here this constant is included always whenever there is no limit. So like here we had a range x1 to x2, and we could subtract hx2 minus hx1 like this. But when we are not given a range, then we just add a constant. And if we had a range, then the constant would simply cancel. So it would be the subtraction of values at the points. Just whenever there are no limits, then you have to add a constant. I hope this is clear. So these kind of integrals in which there is no range over the integration are called indefinite integrals, and integrations of this form where we have a range are called definite integrals. Here are, this is directly taken from the NCERT textbook. Here are some properties of, here are some derivatives and their antiderivatives and some properties of integration, which I will not go over. You can easily read them in the NCERT textbook. And once you are familiar with these properties, then we can proceed to the exercises. So I assume you are familiar with all of the antiderivative and derivative and the properties of integrals. I'll explain you intuitively what does the integral actually mean. I think we are ready to go to the exercises. So the first question in our textbook is integral of sine 2x dx. So one very important thing that you should note is that so you know that you can easily write down. You would have seen from the NCERT examples that yeah, you would have seen from the NCERT examples that you can split an integral in this form easily, and you would know the basic properties of integrals. So I would like to teach you some techniques. So for a basic example, you can have integral. The question 18 is like a basic example where you have integral of sec x times sec x plus tan x dx. You can multiply the brackets and then open them up, split them into addition, and you know the integral of sec square x is equals to tan x. You know that from the antiderivative equation. You know here integral of sec square x is tan x, and integral of sec x tan x will be sec x plus constant because this is an unbound indefinite integration, and I just use the result for sec square x and sec x tan x. Similarly, in question 19, I'll go over questions 1 to 17, but I do want to teach you something, a trick to them. So I'll first go through the basics. The integration of sec square x divided by cosec square x. So you can just simplify. We know that there is no direct formula for sec square x divided by cosec square x antiderivative. So we need to simplify this expression in order to bring it to a form where we know the antiderivative. This is basically what integration is all about. So if we can write sec square x as 1 by cos square x and cosec square x as 1 by sin square x, and then we can write it as sin square x divided by cos square x. This is tan square x. We don't even have the integral, the derivative, antiderivative for tan square x in our formula list or whatever you call it. But we know from the property that tan square x is sec square x minus 1. And if we write it like that, now we have the antiderivative for sec square x and we have the antiderivative for 1 as well. So the antiderivative for sec square x, you know, is tan x, and for 1 it's x and plus the constant. So this way you have to bring down the expression to simpler term. Now we have 20th example. This is also a nice example. So 2 minus 3 times sin x divided by cos square x dx. You can split the terms like this, and you can notice that this is just 2 sec square x dx, and you know the antiderivative for sec square x, and the first integral you can easily solve. The second integral is requires slightly clever adjustment where you can divide the denominator as cos x times cos x, and the numerator will be sin x only, and then you can group them in the following manner. Now you see it will be sec x times tan x times sec x, and this antiderivative we have the integral of the antiderivative of sec x tan x. You know it's sec x only. So we can write here 2 tan x minus 3 sec x plus 3, and thus we could solve this easily. Now you would know how to solve the basic examples. So let us get to a few more bits. So we can even see question 8. So ax squared plus bx plus c dx. This would give us, if we split the terms, ax square integral, bx integral, c integral, and the integral for x square will be ax cubed by 3. You know the antiderivative of x to the power n is x to the power n plus 1 divided by n plus 1, and we have used this property. That's it. So these questions are fairly simple. But for example, you had to calculate the integral for e to the power 3x plus 1 dx, which is the question 6 of NCERT. How would we do it? So it's, I guess there's a 4 in ahead of it also. Yeah. So how would you do it? So you do not have the value of the integral, you do not have the antiderivative for e to the power 3x. You only have it for e to the power x. So in such a situation, what you can do is whenever you are away from an antiderivative by a linear transform. For example, you know the derivative for e to the power x, right? The antiderivative for e to the power x, it's simply e to the power x. You can calculate the derivative of antiderivative of e to the power 3x as just e to the power 3x divided by 3. This 3 came here because there was a 3 with multiplication with x. Let us see some more examples of this. This is a very useful trick when solving questions of integration, and this really speeds things up. So let us try to consider sine 2x. So whenever, so here we see that we know the antiderivative for sine x, but here we are not having x, we are basically having 2x. What should we do here? So in such a situation, let me uh, explain this. If you go to your, yes, so in such a situation, you can see sine 2x. 2x can basically be, so sine 2x dx. Here you can simply write it as uh, 2x. Now, how did we write this? So we know that the derivative of 2x will basically be uh, derivative of 2x will basically be 2 times the derivative of x, and therefore we can write derivative of x as simply derivative of 2x by 2, and if we can further simplify it to just integral of sine 2x divided by d2. Now you can consider 2x as t. So suppose t is 2x, then you'll simply be able to write sine t divided by dt. This is a method called integration by substitution, which I think is not uh, it's covered in future exercises. But for now, you can simply say that that since now you see that the 2 has just basically come out. So sine 2x dx, we have basically reduced it to sine t dt, which is the integral that we know. Yeah, which is the integral that we know, but 2 has come out in the denominator. We have divided by 2 to account for the x which is multiplied by 2. So it might be a little confusing to understand initially. Similarly, in cos 3x, because there is a 3 multiplied with x, we can simply take out the 3 in the denominator and write it like this. Note that this would not always hold true when this would only hold true when we only have a linear x. So if we had that cos 3x square, then this would not hold because x square is not linear, but x is linear, and that is why we can always divide by the coefficient of x to obtain the final answer. And I have explained you the logic there. So if you divide by the coefficient of x and you multiply it and adjust that multiplied coefficient with dx itself, then basically you, I'll reiterate over it. So sine 2x dx, suppose you divide by 2 and you adjust the 2 multiplied with dx, then what you get is basically a form sine t dt where t is 2x. So you have made a change of variable, and there is a division by 2 outside the integral. You can use this property. So one tricky example of this is integral of ax plus b to the whole square dx. There you can see if we treat ax plus b as a quantity and ax plus b square as a function of ax plus b. So here the argument to the function is a multiplication with x, which is the linear multiplication, which is linear. So x is linear and we have multiplied by the constant a. So we can simply just calculate the integral as if we are doing it for x itself. So it would give me x plus b to the cube divided by 3 and divide by the coefficient of x, which is a. Note that b would not have an impact here because b is not a function of b does not have x the second term, it's just a constant and it does not matter. So we'll just divide by a here directly, and we have basically integrated this treating ax plus b as x. So if we treat ax plus b as x, then it would be x cubed by 3. Just replace x by x plus b, so it will be ax plus b to the cube by 3 and divide by the coefficient of x if x is linear, which it is. So it would be ax plus b to the cube divided by 3 a. If you did not want to do it this way, then you could simply expand. So for example, the first question, if you did not want to use this trick or you did not understand it, so then you can simply just write integral of sine 2x. You can simply write sine 2x as 2 sine x cos x. So for example, here you can write, this was our original question. So you can basically write this as, we know from the formula for sine 2x that it is 2 sine x cos x dx. And this we can simply write as, we can see I've written it as 2 sine x cos x dx. Now, if I feed some variable t. So basically, t is equals to sine x, for example. Then we can write what? We can write integral of 2 times t, t is a sine x, into cos x dx. Now you should note that the derivative or the derivative of sine x with respect to x is cos x, and therefore, thus we can also write what can you can write that cos cos x dx is equals to d sine x. We'll just simply transfer the dx to the right hand side to obtain cos x dx is d sine x. So, and sine x is t. Since sine x is t, therefore we can write what? We can write that dt, where sine x, we can write cos x dx is dt from this equation. And if we put this value back into the earlier expression, this one, so we can now write 2 into t into cos x dx will be nothing but dt, and this from this it becomes pretty easy to solve. We can just write it as 2 times integral of t dt, and this we know from our basic formula that this would be which we can write as now the 2 would cancel, and hence we would have we can write it as t square plus t, and t here is nothing but sine x. So we can write here sine square x plus c, which is sine square x plus. So this is how we can solve it by expanding sine to x. I showed you another method by taking advantage that x is linear here, and therefore we can treat 2x as simply x, write the expression, and divide the final answer by 2. And this is how we can basically approach all integration problems. Let us try to solve another example. So question number 5 from your NCERT, it would basically be this integral of sine 2x minus 4 e to the power dx. So we can write it as integral of sine 2x minus 4 times integral of e to the power 3x. And now you can see that integral for sine 2x. So let us write it using the trick that I showed you today. So sine 2x, as you can see, it is linear in x. The argument of sine is linear in x. So since it is linear, so we can simply treat 2x as a single quantity as x, and the integral of sine x it would become then, and integral of sine x we know is minus cos x. So we can write it as minus cos, but remember in the final expression it would still be 2x. And since the coefficient was 2, and so we would derive it, we would divide it by 1 by 2, like this, minus 1 by 2 cos 2x, plus some constant. We'll include the constant after evaluating the second integral, and this would basically be 4 into, so e to the power 3x dx integral. So we know the integral for e to the power x, and since the argument for the exponential function is linear, so we can simply assume that we can simply substitute 3x for x and write the answer, which is e to the power 3x. Again, we'll just put 3x in the final thing, no matter what we treat it as while polynomial integral. So e to the power 3x, and since the coefficient of x is 3, we'll have to divide by 3 here. So we add a 1 by 3 here, and plus some constant. So this would be our final answer to this problem. minus 1 by 2 cos 2x minus 4 by 3 e to the power 3x plus 3. This trick will be very useful for you in competitive examinations because uh, there you would not be dealing with substitution all the time. You can directly see if the argument of function is linear, then we can directly uh, use it in this manner. So let us see an example where it does not work. So let us see an example where this trick does not work. So suppose we are asked to evaluate integral of sine x square dx or into 2x dx. Now here you cannot use this trick. Here we cannot use the trick because why? Because the argument to sine x square is into the sine function is not linear in x because it is x squared, and therefore we cannot use this trick of just writing x square as x. This will not work. We can only write 2x as x, 3x as x, even 3x plus 5 as x. So it would only work if we instead had uh, a linear function of a function of linear function of x as input. Later I'll show you examples where it will work, an extensive list of examples. So here how are we going to solve this integral? So this integral can be basically solved by taking x square as t. So this integral can be solved by taking uh, x square as t. So if we take x square as t, then we can simply write this as integral of sine t into derivative of t. So how did this come about? Let's see. We have x square is t. This means that derivative of x square is derivative of t equals to 2x dx is dt. And since 2x dx is dt, we can directly put its value from 2x dx here to write it dt. And then sine t dt, we have the answer to this. This would be uh, minus cos t to minus cos t plus some constant. So I hope you understood. So uh, a list of examples where the linear trick, I'll call it linear trick, would work. So if we had, for example, suppose we had integral of sine of suppose x 2x plus 5, then we can very well use this trick. Suppose we had integral of e to the power, I don't know, 5x plus 7, it would work. You see that the argument to the functions there are linear functions, are themselves linear in x. So uh, more examples like suppose we had integral of tan of 3x dx. We would again be able to use this thing. So as you can see, we can I hope you would have understood when can be used. So this can simply be written as, now we'll just solve these integrals very fast. So since 2x plus 5 is linear in x, so we can simply keep it as x here, or basically as integral of sine t dt, and we can divide it by 2. So sine t dt is nothing but minus cos t. So minus cos t, t is 2x plus 5, and since the coefficient of x is 2, hence we would use this. For the next example, here we know that the argument to the exponential function is linear in x, and it's 5x plus 7. We'll treat 5x plus 7 as t. Evaluate e to the power t dt and integral. What is it? It's e to the power t itself. You can write it as e to the power. T here is 5x plus 7, and since the coefficient of t is 5, we'll write it as plus of x. Never forget this one. So yeah, similarly for tan 3x, we can write it very similarly. So I hope you would have got a basic idea of how things are working here. And that was basically the complete exercise. Most of the examples were very repetitive, but some examples which actually had something important, I have covered all of them. Yeah, the last example is also good. Here we have derivative of fx equals to 4x cube minus 3 divided by x to the power 4, and we are given that f2 is 0. So if we are given the derivative of the function with respect to x is this, we can transfer dx there, and we can integrate both sides to obtain. We have put the integral sign on both sides. The derivative of fx would just integrate to fx. I just showed you there in the notes that the derivative of fx does integrate to fx, and and we can just perform this integration very easily using the basic formulas for the antiderivative of x to the power n, and then we'll have fx is x to the power 4 plus 1 by x cube plus c. Now we are given that f2 is 0, so we can put so the only variable here is c, so that's why I told that c is very important. We do not know the value of c here. To get the value of c, we are given another constraint that f2 is 0. Hence we can write f2, which is 2 to the power 4 plus 1 by 2 cube plus c, and the 16 plus 1 by plus c is 0. And we obtain the value of c as minus 129 by f. And I think this was one of the options. So this would be your final answer. So the c actually, even though many times we forget it, but it is actually very important. It is an unknown variable whenever we are using unbounded or indefinite integration, then it is a variable. And in order to get the exact value of c, we need more equations or more constraints. So here we are given that f2 is 0, hence we could calculate the value of c and get the exact value of the function. Without this, we could not have solved exactly for f. So I think that was all from my side. Since you would have got what I got the basic of integration in the XII 7.5, and I hope you would have understood this trick. So I think that's it for today. Thank you so much.